Hello and welcome to this FMSP online revision recording for the OCR specification for the module M1 Mechanics. And this topic is force as a vector. And as we look at the specification, there are three particular points. The first is the idea of representing forces with vectors. That is, a vector quantity as opposed to a scalar quantity. That is one which has magnitude but no particular direction, such as perhaps time or temperature. Instead of that, we're typically representing forces with a magnitude in a given direction, which may be specified with an angle or maybe a bearing. And the second idea is the idea of the resultant. Now, the resultant of two vectors is simply the language we use when we're talking about vectors for the sum. We're adding, and this is the sum that we're finding. When adding vectors, the sum of two vectors is the same as the result if we have the first vector followed by the second vector and join the beginning of the first to the end of the second. So this vector would be the resultant or the sum. And our third point in the specification is the idea of resolving a force into perpendicular components. Those components might be horizontal and vertical, if that suits the question. On the other hand, for forces where an object is at rest on an inclined plane, we might prefer to take the direction of the plane itself and a direction at 90 degrees to the plane, parallel to the plane and perpendicular to the plane. The shorthand I always use for these is this one for parallel and this sign with a little 90 degrees angle in it for perpendicular. You'll notice, by the way, from this section that we don't need to write in I and J form or column vector form in module M1. Most of the time we're just considering the component in a particular direction, so I shan't in the rest of this recording be using I's and J's or column vectors. So now some key points. I hope you're all good at finding the perpendicular sides when you're given the hypotenuse of a triangle and one angle. The adjacent side is always connected to cosine of the angle and the opposite side with sine of the angle. So the x length here is the hypotenuse times cosine of theta, and the opposite side r times the sine of theta. Now here's a situation where we're taking perpendicular components, but the force itself is already vertical. And here is the component next to the angle, so that's 147 cos 30. And the one opposite the angle, 147 sine 30. And it's so important always in mechanics to draw a diagram big enough to label all the components and all the angles so that you can read them clearly. So we have finding the resultant of two forces, and remembering resultant simply means the sum of two or more forces. If the two forces are perpendicular, we can simply use ordinary Pythagoras and trigonometry of a right-angled triangle. If the forces are at another angle other than 90 degrees, we may need to use the cosine rule or the sine rule. And if there are more than two forces, the simplest way is probably to find each one in component form and add them up, so we have a single resultant in each direction in component form, and then use ordinary Pythagoras and trigonometry. And I've chosen some questions from recent exam papers to exemplify each of these points. Here's the first one, and it's very nice and straightforward. You'll notice it's question 1 from this particular paper, so it's one where the examiner hopes you'll have a good introduction to the paper and be able to cope perfectly well. Two forces have magnitudes 8 newtons and 15 newtons. There's no mention of the direction, except that the two forces are perpendicular, so I can draw them really anyhow I like. So I chose to draw the 8 newtons force as horizontal and the 15 newtons force as vertical. Of course, in this position I can't find the resultant because I need to consider the resultant with one force followed by the other. So let's draw 50 newtons at this end now, and that diagonal line would be my resultant. Typically on diagrams I show the resultant with a double arrowhead. Now we don't know the length of that line, although looking at the very badly drawn triangle we can see that it's going to be longer than 15. And then we'd like to find an angle. Find the angle which the resultant makes with the larger force. Well, on my diagram I automatically think it's going to be that angle, but that is the same as the angle in here, so depending on the way you think about it, you might like to consider the angle inside the triangle. Okay, this is simply a right-angled triangle with ordinary Pythagoras and standard trigonometry. So the magnitude of the force is the square root of 8 squared plus 15 squared. And that very conveniently is exactly 17 newtons. And then as far as the angle is concerned, I'm looking from this perspective here, so opposite is the 18 newtons and next to it the 15 newtons. So tan of theta equals opposite over adjacent. That is 8 over 15, and therefore theta is inverse tan of 8 over 15. I calculate that to be 28.1 degrees, giving my answer to 1 decimal place. And there's our first example using standard, Pythagoras and trigonometry of a right-angled triangle. Now here's a harder question. I have 3 forces and a horizontal force of 8, a vertical force of which I don't know the magnitude, and then a third force of 10 newtons at an angle that I don't know. However, I do know that the 3 are in equilibrium. So it's going to suit me here to take components which are horizontal and vertical of the 10 newton force and consider, because it's in equilibrium, the total components in any direction to be equal to 0. That's the same as saying in this case lefts equal rights and ups equal downs. Okay, let's look at the diagram alone and just tidy it up a little bit. First of all, I want to show the components of the 10 newton force. It's a bit of a fiddle that the 10 newtons is written there. I'd rather see the 10 newtons over here as the hypotenuse of this right-angled triangle. And then looking at components, I can see, starting from this point and putting the directions carefully in, that to the left it's 10 times cosine of alpha because it's next to the angle, and the vertical component 10 sine alpha because it's opposite the angle. Okay, looking first horizontally, I've got 10 cos alpha to the left equals 8 newtons to the right, and they're equal because the forces are in equilibrium. That gives me cos alpha equals 0.8. And digging out my calculator, alpha is cos to the minus 1 of 0.8. That angle is 36.9 degrees to 1 decimal place. As soon as I saw that on the screen, I thought I recognised that, so we'll come back to that point in a minute. And now let's look vertically. Now I've answered the question in the order it was asked. The first part asks for the angle alpha and the second for the force F. when I consider vertically, I've got f upwards equals 10 sine alpha downwards. And if I'd tried to do this first, I'd have found myself with two unknowns, so I did need to find the angle before finding the magnitude of f. So therefore I know from my previous working that f is 10 times sine of 36.9 degrees. But I've handily kept that on the calculator so that I can use this to full accuracy and not simply type in 36.9, which might lead to a small error. That gave me F equals exactly 6 newtons. So there's my angle alpha and my force F. And before leaving this question, I just want to point out what you've probably noticed already, which is that if 10 cos alpha equals 8 and 10 sine alpha equals 6, we have over here 6, 8, 10 as the three sides of my triangle. In other words, it's my familiar 3, 4, 5 triangle enlarged by a scale factor of 2. Let's now look at another question, and this one considers two horizontal forces of magnitudes 12 newtons and 19 newtons. Now don't be confused because the question says two horizontal forces. They mean forces acting in a horizontal plane, but we're not going to represent these two forces with lines which look horizontal on this page. Just want to clear that up because the question could be read in a misleading way. Because we're told the angle between the two forces is 60 degrees. Well, as I don't have any other information, I might as well draw the 12 newtons force in this direction. And the 19 newtons force, so it's got to look longer and at an angle of 60 degrees. Immediately there's a misconception that I want to address, and that is some folks are going to think that that line joining the ends of the two vectors is the resultant. No, no, no. Because I need to consider the 12 newtons force to be followed by the 19 newtons force. So on my diagram it needs to look like this. I'm going to redraw the diagram in a moment, but I just want to point out a couple of obvious things. If the resultant starts at this point on the left and ends at the end of the vector here, first of all you can see that the magnitude of that must be greater than 19, and that the angle it makes down here with the 12 newtons force has to be less than 60 degrees. That'll be useful information to check my answer when I've got one. So now I'm going to redraw the diagram. Try and make it just a little better this time if I can. 12 newtons, and then over here the 19 newtons. It's always worth getting your diagrams approximately in proportion, because it gives you some sense of whether or not your answer is correct at the end. So there's my resultant, and the angle I'm trying to find in here that I already know is less than 60 degrees is alpha. And the 60 degrees that I previously had between the 12 newtons and the 19 newtons is now over here. That means I do know an angle inside the triangle. It's 120 degrees. Well, I've got a triangle which is not right angled, and so I'm going to use the cosine rule and the sine rule. So first of all, the cosine rule. I'm using this first because I can see I've got two sides I know with the included angle. And the cosine rule, I always memorize and use this version: a equals b squared plus c squared minus 2bc cos a. And of course, depending on how your triangle is labelled, you know you can change this to make two other versions, such as b squared equals c squared plus a squared minus 2ca cos b, and so on. But if I simply choose to label the known angle as A, which I can choose to do because there's no labelling on this already, then the version I've written down will work. I've made that B and this C, and the side opposite angle A is here, and that's my unknown length I'm trying to find. Opposite angle B is this side, so B is 12, and opposite angle C is this side, so C is 19. Okay then, so simply using the information from the diagram, I've got A squared equals 12 squared plus 19 squared minus 2 times 12 times 19 cos 120. I'll just record the fact that A squared comes out exactly to be 733, because that'll save me losing accuracy perhaps at a later stage in the calculation. And the square root of that is 27.1 newtons to 3 significant figures. But in the later calculation I'm going to use square root of 733 to save any loss of accuracy. Okay, now I need to find the angle alpha, and I'm going to use the sine rule. Now I know which angle I'm trying to find. It's angle C. So I'm going to write the sine rule in the form sine C over side C equals sine capital A, because that's the other angle that I know, over side A. So sine of alpha over C, which is 19, equals sine of 120 degrees over A, which is the square root of 733. So I'm going to write this all in one step. Alpha equals, well, I'd need to multiply this side by 19 and then find inverse sine of all of that. And alpha comes out to be 37.4 degrees. But don't forget that there are two solutions in the range 0 to 180. But it has to be this one because it's the angle which is smaller than 60 degrees. And from my diagram, it does look like it could be 37.4 degrees. I have one more point to make before leaving this example, which is this isn't the only way you could choose to do this question. You could have chosen to split the 19 newtons force at 60 degrees into a horizontal component and a vertical component, and then used the overall horizontal length and the height and ordinary right-angled trigonometry in Pythagoras. Okay, let's move on to our last exam question. And once again notice 3 horizontal forces, and they don't mean that a horizontal line on this diagram is horizontal, they mean you're looking down from above at 3 coplanar forces that are all at a horizontal level. And now we've got bearings involved. North, 0, 0, 0 degrees, the 9 newtons force going west at 270 degrees, and then the 5 newtons at a bearing of 150. We've got 3 tasks to do. The first one is show the component of the resultant of the 3 forces along bearing 270 has magnitude 6.5 newtons. Now I know I'm going to be using H and V to mean H and V horizontal and vertical as I look at my diagram, but just bear in mind the wording of the question tells us all 3 forces are in a horizontal plane. So I'm going to resolve horizontally to find the overall component along the bearing 270, and then to find the component along this bearing I'm going to consider the forces vertical on my page, and lastly I'm going to put those together to find the magnitude and bearing of the resultant of the 3 forces. Okay. What I need to do is split this force into two components, downward part and that part to the right, and I'm given the 150, so that angle in there, which I can't quite squeeze into the diagram, is 30 degrees, making the component next to the angle 5 cosine 30 degrees, and that opposite the angle 5 sine 30 degrees. Let's correct my handwriting there. So looking at those components horizontal to my page and taking a westerly direction, I suppose, which is along the bearing 270, which they ask us to do, which feels a bit counterintuitive because you might have preferred to go to the right rather than the left. Well, we have 9 in the direction 270 minus 5 sine 30 in the opposite direction. Sine 30, you might know, is 0.5. Sorry about that, I'm just going to change that. So that's 5 times 0.5. This is 9 take away 2.5, and that conveniently gives me exactly 6.5 newtons due, well, 270. I'm going to make a little note to myself, that's west. Good. Well, that's what they told me to expect to find. Now looking vertically and taking north as my direction, or along a bearing 0, 0, 0 as they ask, well, we've got 12 in that direction minus 5 cos 30 in the opposite direction. That doesn't have a nice convenient answer. It's 7.66987291, and that's the end of my display on the calculator. So 7.67 newtons to 3 significant figures, but as I'm going to use that number in the last part of the question, I'm going to keep the exact form on the calculator so I can use the answer button and not lose accuracy for the final part of the question. Here we go then. What we've discovered is we can replace that system of 3 forces with 2 forces, one in the direction 270 of 6.5 newtons, and a second one of magnitude 7.67 to 3 significant figures along a bearing 0, 0, 0. And now we're asked for the magnitude of the resultant and the bearing of the resultant force. So I need to copy my 7.67 force across to the right here and complete that triangle. So there's my resultant, and I can see the direction it's facing in. The bearing required is going to be the angle, well, I'll label alpha in there, but don't forget it's going to be 360 minus alpha for the complete bearing. And as I'm finding alpha there, perhaps I might complete the rectangle here and put the 6.5 up there. That'll make it easier for me to consider maybe this triangle, and I've got all the measurements in one place where I can see them. First part then, by Pythagoras. Simply looking at the lengths, and I'm going to write f for my magnitude of my resultant. F squared is 6.5 squared plus 7.67 squared, and remember to keep and reuse the exact value, not the 3 significant figure version that you've written down. And the answer is 10.1 newtons to 3 significant figures. Looking at my diagram, I think that's believable. And then finding alpha, I use the fact that tan of alpha is the opposite over the hypotenuse. Well, the opposite is the 6.5. I'm sorry, opposite over adjacent. Opposite is 6.5, adjacent 7.67. So tan of alpha is 6.5 over, and don't forget, use the exact value again so you don't lose accuracy. So alpha is 10 to the minus 1 of that amount. And that gave me an angle of 40.3 degrees to 1 decimal place. Well, they asked for it as a bearing, and the bearing is clearly going to be this angle subtracted from 360. And that gave me an answer of 319.7 degrees. The question doesn't tell me the accuracy for this answer, and the standard rubric on the front page of the exam says 3 significant figures, but I'm going to leave it as 319.7 because we know that angle and this one have to make 360, and I personally feel that the level of accuracy for angles is best given by the number of decimal places, because angles range from 0 to 3 degrees up to angles with 3 whole number figures before the decimal point within a complete turn. However, the mark scheme I see accepts 320 as the bearing. Well, we've taken several different approaches to dealing with forces and finding resultants, and I know you'll get lots of practice because this particular skill crops up again and again in mechanics questions.